I do appreciate the fact that it's right after lunch, and this is the time when people are most likely to fall asleep. I'm going to take certain steps to try to prevent this. Now, some of you know what this is. If you don't know what this is, ask someone who does, such as Agnes, Irina, Mike Hill, Hood Chatham, and Jolie Shu, and Danny Shee, and so forth. A lot of victims of this thing. When many years ago, we had 4 kids in the house, and it was always a struggle to keep them under control. And my wife would always threaten to beat them with a wooden spoon. She never actually did it, but she was constantly threatening. It was an intimidation thing. So this is my wooden spoon. Now, instead of using the wooden spoon, I'm going to do this. So you're going to see a video made by Niles Johnson, which is fun to watch. Probably won't show the whole thing, but anyway, I hope this gives you a little wake up. Okay, you can probably guess what this is about. This is about the Hopf map. So on the lower, down here, this is a picture of the 2-sphere, and these circles up here represent the pre-images of the points as they move around the 2-sphere. I think this is a really cool video. I really admire Niles for making this. And if you think this is cool, you should see his video about the Milner's exotic 7-sphere. Okay, I think that's enough of that. Okay, so now on with the talk. Okay, so here's a picture. You've probably seen a picture very much like this before. This is a diagram of A of 1, the subalgebra generated by Sq1 and Sq2. I was hoping Leanne Merrill would be here. She's a new PhD at Oregon, and she has this diagram tattooed on her arm. So she owns it. But she's not here, so I'm going to have to make do without her. Now, there's one thing different about this diagram from her tattoo, and that is that the line in the middle is red. And there is a reason for that, and that will come out during the talk. Now, this talk is about equivariant homotopy theory. I'm not going to go through all the song and dance about the basics of equivariant homotopy theory. I hope you know something about it. The group in question is always going to be C2. One of the first things I learned about this subject was there's an introduction written by Greenlease and May, and early on, at the very beginning of it, they say, the problem with equivariant homotopy theory is not in the complexity of the group. You can do it for very complicated groups, but the complexity of the group is not the issue. It's the mere fact that the group is non-trivial is the issue. And even with a group of order 2, even if you look at examples of order 2, the group of order 2, you can find all sorts of conceptual problems that need to be addressed. So I'm going to say just a little bit about some of it, but not very much. So part of what you need to understand is the orthogonal representation theory of the group in question. Now, for this group, it's pretty simple. A finite dimensional orthogonal representation of C2 always has this form, where m and n are non-negative integers, and sigma denotes the sign representation. So this means that we've got the group is acting on Rm plus n, and if you diagonalize the matrix, you'd find that n of the entries are negative and m are positive. Now, if you've got a representation like that, here's some notation that's common in the subject. S parentheses V stands for the unit sphere in this vector space. So it is preserved by the group action. So if V is this representation, you get a certain group action on this sphere. And the underlying space in this case is the unit sphere in Rm plus n. So that's a sphere of dimension 1 less. Now, a very similar symbol is S upper V. This means this stands for the one-point compactification of the vector space, and that also has a group action on it. The point at infinity is fixed, as is the origin. And so in this case, the underlying space is Sm plus n. And I'm going to use these things from time to time. Now, here's a picture of the simplest non-trivial example, S upper sigma, which I may refer to as the twisted circle. So it is a circle where the group acts by reflection through a vertical line. So there's two fixed points that are indicated here in blue. The north and south pole are fixed, and everything else gets swapped around. Now, I'm going to tell you something about the Hopf map from an equivariant point of view. This is a little, you might think of this as a little appetizer. This is a very interesting phenomenon in equivariant homotopy theory that surprised me when I first learned about it. So here it is. So remember, you've heard of the Hopf map before. Here's a shot from Niles's video. So it is the map from S3 to CP1. So you think of S3 as the unit sphere in complex two-dimensional vector space. A point on that sphere defines a complex line through the origin, and the space of complex lines through the origin is the projective line, which is homeomorphic to S2. So this is very familiar, I hope. Now, here's something we know about this. If you compose various suspensions of it, as indicated here, that composition is known to be null homotopic. This has been known for, I think this is probably due to Toda. But anyway, this has been known for 50 years. This composition is null homotopic. Now, what I'm about to explain to you is that there is an equivariant form of this in which no composition like this is null homotopic. So here's how we do this. Both the source and the target of this map have a C2 action defined in terms of complex conjugation. You can conjugate the vectors in C2, you can conjugate the complex lines in CP1. And in both cases, both of these spaces are spheres, and both of them, as C2 spaces, they are the kind of thing I discussed on the previous page. So on this side, we have the unit sphere for 2 plus 2 sigma. The complex vector space, let's see, the complex numbers itself is, as a representation, it is 1 plus sigma. You have conjugation, and conjugation fixes the real line, acts as the sign representation on the imaginary axis. So that representation is 1 plus sigma. This is twice it, so this is 2 plus 2 sigma, and S3 is the unit sphere in it. And that unit sphere happens to be the same thing as this space. And then the space on the other side is S1 plus sigma. That's the one-point compactification of the complex numbers. So that's S1 plus sigma. So we take the same map, but now I'm putting a bar over it to emphasize that now we're thinking of it as an equivariant map. It is an equivariant map. It respects the C2 action on the source and target. Now, one of the main tools in equivariant homotopy theory is to, if you've got an equivariant map between G spaces, then you automatically, for every subgroup H of G, you automatically get a map from the set of points that are fixed by H in the domain to the corresponding space in the target. And if you want to show something about the map that you're dealing with, like whether it's null homotopic or a homotopy equivalence or whatnot, it suffices to show that it satisfies that it has that property for all fixed point sets, for all subgroups. Now, in this case, there's only one proper subgroup, and that's the trivial subgroup. So if you work out what the fixed points are of these two spaces, in both cases it's the circle, and the map that's induced on the fixed point sets is the degree 2 map. Now, I think if Dan Isaacson were here, he would tell me, it's really the -2 map. And I'm not sure about that, but it won't matter for what I'm about to tell you. Anyway, the key point here is that you can iterate this map until the cows come home, and it'll never be null homotopic. And so that means you can iterate this map till the cows come home, and it will never be equivariantly null homotopic. So I think I say all that on the next slide. I left out the cows, but anyway, there you go. So here's an iteration. Now this iteration involves the twisted suspension, which is smashing with the twisted circle. The ordinary suspension is smashing with the ordinary circle. The twisted suspension is smashing with the twisted circle that I showed you on the first slide. And so you need to see you're applying twisted suspensions to these spheres to make this work out right. So you can have any number of iterates up here, and in each case, the fixed point set is a circle, and you get the degree 2 map. So you could iterate this any number of times, and it's an essential map. So this means that if you pass to the stable category, you discover that the equivariant Hopf map is not nilpotent. Now, in the classical case, it is nilpotence. The Nishida's theorem or the nilpotence theorem says it's nilpotence, but in the equivariant world, it isn't. And when I learned this a few years ago, I thought, boy, this is really strange. This is a very different universe. There's stuff in the equivariant world that you don't see in the ordinary world. Anyway, this is a simple example, and it'll come up. You'll see this later in the calculation I'm going to describe. Okay, so now I'm going to describe the equivariant mod 2 homology of a point. Now, the first thing I have to point out is that in ordinary homotopy theory, you deal with graded groups. You have graded homotopy groups, graded homology groups, and so forth and so on. And they're always graded by the integers. In the equivariant world, you have things that are graded by the orthogonal representation ring of the group in question. And in our case, that's the orthogonal representation ring, I guess I didn't say it, but the orthogonal representation ring for C2 is a free abelian group on 2 generators, namely 1 and sigma. And sigma squared is 1, but we never actually use that multiplication in these things. But anyway, you get ROG-graded homotopy groups, homology groups, and cohomology groups. So you can speak about oh, it has a typo here. I'm sorry. That's supposed to be a star rather than an asterisk. I made a mistake. I'll get to that later. Well, I'm going to tell you an oddity now. The symbol I should have used was \STAR, which produces a 5-pointed star in TeX. Now, the odd thing is, if you look on your keyboard, if you look at the asterisk on your keyboard, you will discover that it has 5 points. And if you type it in a text editor, you will get a 5-pointed asterisk. But if you put it in a TeX document, you'll get a 6-pointed asterisk like I do here. And if you write it on the blackboard, you'll get a 6-pointed asterisk. I don't know anybody that can do 5-pointed asterisks on the blackboard. It's really, really difficult. Okay, so we've got that we can talk about the homology of a point. This was supposed to be a star, which indicates ROG grading. Or we could talk about the cohomology of a point, and they are the same, except they're oppositely graded. The grading in cohomology is the negative of the grading in homology. Now, there's 2 elements of interest in constructing, in describing this thing. One is this map. Now you notice I put it in blue. I'm going to use that. These things are going to be color-coded, I hope, consistently throughout this talk. So this is the twisted circle that I showed you before, and this is the fixed points. This is the inclusion of the fixed points into the twisted circle. That's certainly an equivariant map, and Now notice that if we forgot about the group action, we'd be mapping S0 into the circle, and that map would, of course, be null homotopic. But not now. This map is not null homotopic as an equivariant map. There's no way to slide the North Pole down to the South Pole to make, you can't do that equivariantly. Anyway, this map is essential as an equivariant map. And okay, so that gives you an element, stably this gives you an element in pi minus sigma of the zero sphere. S minus 0 is my notation for the sphere spectrum. For reasons that I'm not going to explain in this talk. You can ask me later if you want. Okay, and so you can go from the homotopy of the sphere spectrum to the homology. There's a Hurewicz map, and I'll use the same symbol there. And I'm going to sometimes refer to this as the polar generator, and that's because it involves the north and south pole. It's also known as an Euler class. Okay, that's one class. Now, it's possible to calculate the equivariant homology of the twisted sphere. I'm not going to give you a textbook explanation of how that's done, but I think you could probably be willing to believe that the mod 2 H1 of the twisted sphere, suitably defined, is Z mod 2. And so I'm going to give the name, I'm going to give a name to the generator of that group. I'm going to call it U, and U will always be written in red. Okay, so if we do this in cohomology, so now I've got superscripts instead of subscripts, now the gradings are reversed. Before A had degree minus sigma, now it has degree sigma, and U is also reversed. Okay, now there's a parallel between this and motivic homotopy theory. Now, before you ask me any questions about motivic homotopy theory, I have to say something. Now, I don't like to brag, but I can assure you that among the 4 authors of this project, I am the one that knows the least about motivic homotopy theory. So, if you have questions about the motivic side of this, ask one of my co-authors. 2 of them are here in this room. Okay, so these same elements occur in real motivic homotopy theory, but they have different names. A is known to motivic homotopy theorists as rho, and U is known as tau. And I wrote this dictionary over here on the blackboard so you can remember it. And they also have a different grading convention. See, in the equivariant world, you have things graded over RO C2, the orthogonal representation ring. The motivic guys like to give everything a bi degree, and there's a rule for translating, and that is that the motivic degree, stem, and weight, and if the motivic degree is SW, that corresponds to this element in the representation ring. So the weight is the number of times that sigma occurs in the picture, and the stem is the total of these 2 indices. In other words, the dimension of the underlying representation is what the motivic people call the stem, and the weight is the number of times that sigma appears. Now, rho. So this happens in real motivic homotopy theory. When you pass to complex motivic homotopy theory, the element rho, which is an alias for A, disappears. It becomes 0. So the following things are known for appropriate versions. There's a version of the sphere spectrum in the real and complex motivic worlds. Don't ask me how it's defined. But anyway, we know that in the complex motivic world, the cohomology of a point, the mod 2 cohomology of the sphere spectrum is polynomial algebra on tau. In the real case, we get a polynomial algebra on rho and tau. So rho and tau are these elements here that correspond to A and U that have these geometric descriptions that I showed you before. Now, in the equivariant world, I'm not having any subscript here. So the the equivariant mod 2 cohomology of the sphere spectrum contains the polynomial algebra on A and U. So it contains something isomorphic to the real case, the real motivic case, but there's more. And there's another piece known as the negative cone. And it consists of fractions that look like this. Now, it's a little hard to, this is kind of weird, but these things remind me of chromatic fractions. The BP homology of the K local sphere has a similar description. But anyway, the best way to show you this might be a picture. So here's a chart indicating this. So this is, okay, so here's, okay, the red lines indicate multiplication by U, the blue lines indicate multiplication by A, and the point xy in this chart represents this bi-degree. So the horizontal degree is the total dimension of the representation, and the vertical degree is what the motivic people would call the weight. And so this piece up here is a polynomial algebra on U and A, and this piece down here is the negative cone. So everybody in the negative cone is killed by some power of A and by some power of U, and everybody in the negative cone is divisible by U and divisible by A. Now, yes, I have this displayed on another screen, so if you ever want to see it again, I can shift to it instantly. Okay, now I'm going to talk about the Steenrod algebra in this world. So, the motivic Steenrod algebra, mod 2 Steenrod algebra was first described by Voevodsky around 2000, and about the same time, Hugh and Kriz described the equivariant, the C2 equivariant case. And the answers are essentially the same modulo translating the notations. They get the same answer, and I'm going to describe it. I'm going to describe it in two different ways. First, I'm going to describe it as an algebra generated by squaring operations, as in the classical case. And then I will tell you what the dual algebra looks like. Okay, so you have squaring operations that I'll call square K. Now, you have to be a little careful because the degree of square K is indicated here. So if K is even, the degree of if K is 2i, the degree is I times 1 plus sigma, and the degree of square 2i plus 1 is 1 more than that. So it's a little bit different in that sense. Now, as in the classical case, square 0 is 1, and the algebra, this Steenrod algebra, acts on the coefficient ring. So here's some formulas that describe this. At first, it acts, now remember, W was the placeholder for the negative cone. The Steenrod algebra acts trivially on A and W, but it doesn't act trivially on U. So square 0 of U is U, square 1 of U is A, and the higher squares kill U. Now, you want to be able to describe what it does to, say, a monomial in A and U, and for that you need a Cartan formula, which I'll describe in a moment. But to refresh your memory, this is the classical Cartan formula here. This tells you that square n on a product xy can be expressed like this. Now, the Cartan formula in this case is sort of like that. But anyway, I'll start with this. So first, this is half of the Cartan formula. This tells you how an even square acts on a product. Now, you have this sum, which is similar to the sum on the blackboard. Now, notice here that these exponents are all even, and here's the sum where the terms have odd exponents. and there's a factor of u in front of it. That u has to be there in order to make the degrees come out right. That u has to be there if this expression on the right is going to have the same degree as the expression on the left. Okay, so that's the Cartan formula for even squares. Now, I could just write down a similar formula for odd squares, but I'm actually going to derive it. I'm going to give it to you. So here's here's the deal. Square 1 has the properties you would expect. It is a derivation. Its product with itself is 0, and and square 1, square 2i is square 2i plus 1. This is exactly what happens with the classical Steenrod algebra. No surprises here. But the surprise is that square 1 of u is a. Now, if you apply square 1 to both sides of this equation, you get this. So this is the Cartan formula for an odd squaring operation. And notice it's got a term a in it. This is the term you would expect. This is the sum you would expect classically. But there's an additional term here. Now notice that the sum of these exponents is not this number. It's, what is it? 1 less. These add up, these two exponents add up to 2i, and here we've got 2i plus 1, and there's a factor of a in front of it. Now, in general, when you have a formula in this C2 equivariant world, if you set u equal to 1 and a equal to 0, you will get the classical, that'll take you to the classical case. So if you do that here, that means this unexpected term will go away, this u will become 1, and you'll have the classical Cartan formula. But this has a little more information than the classical Cartan formula. Okay, now I'm going to tell you about the Adem relations. The formula for the Adem relations, now I wrote the classical, here's the classical Adem relation. You've seen it before, but if you're like me, you don't remember it. I don't know that, not sure I've ever met anyone who's actually memorized this formula. Don't feel bad if you don't remember it, but there it is. Okay, so it turns out that the formula depends on the parity of m plus n. So here it is in the even case. Now, when m plus n is even. Now, this formula looks very much like this formula, except you'll notice that there's a factor of u in certain cases. And again, that factor of u has to be there to make the degrees come out right. Now, I don't have an easy explanation of the next formula I'm going to show you. It's more complicated. When m plus n is odd, here it is. So in this case, this is the classical formula that's on the blackboard. But then there's another term here that it has a factor of a in it. And anything that has a in it is going to disappear when you pass to the classical case. Now, this formula was not easy to come by. You've probably been told, as I have, that the Adem relations are somehow equivalent to the structure of the Dualsteen rod algebra. Clearly, one determines the other. And I confess, I have never tried to derive one from the other, and I've heard that it's a very difficult exercise. Now, what happened historically is that Voevodsky worked out the formula for the Dualsteen rod algebra, which I'll show you in a minute, and then he tried to do this exercise of deriving the Adem relations, and he got the wrong answer. The answer that's in his paper is clearly wrong because the right and left-hand side don't have the same degree. He got it wrong. A few years later, Jeffrey Powell wrote a paper on this subject, and he got it wrong too. And I learned this. I found his paper by snooping around on the internet, and I wrote to him about it, and he says, no, I didn't get it right either. So the person who got it right is, at least I hope it's right, is Joel Ryu. And it's a paper in 2012. So that's where I got these Adem relations. Now, Dan Isaacson says there's no point in studying these Adem relations because all the information you need is in the Dualsteen algebra. So, okay, so now I'm going to describe, here's some sample Adem relations. So square 1 square n is what you'd expect. Square 2 square n is pretty much what you'd expect, except there are some u's where they have to be. And square 3 square n has some unexpected terms involving a, as you see here. Now, let's go to the, now I'm going to tell you about the subalgebra generated by square 1 and square 2. So here's a picture of it. Using the same, it has the basis you'd expect. It's a free module over the coefficient ring, a free module of rank 8, as you would expect. And the basis elements are shown in this chart using the same grading conventions as before. So this is square 1, this is square 2, this is square 1, square 2, so this guy's square 3, this is square 2, square 1. This one is square 1, square 3. Now, I must have written down what I'm about to tell you. In the classical case, square 2 is square 3, square 1. That's sort of the first Adem relation you ever learn. The first really interesting Adem relation. Square 2 is square 3, square 1. But in this case, there has to be a factor of u in the picture. And that's why I've drawn a red line here. So square 2 in this picture should actually be up here. Square 2 would be up here, but it is in fact u times this element, which is square 3, square 1, right? Okay, so that's a picture of the Steenrod algebra, and here's another diagram. So this is Leanne's tattoo, and this is the C2-equivariant analog of it so this line is in red because it involves a factor of u. Okay, now here's a chart that shows how these two operations act on the coefficient ring. Now, here's the chart of the coefficient ring that I showed you before, and now in the chart I'm going to show you now, the red and blue lines are removed, and instead we have lines indicating the action of the square 1 and square 2. So the horizontal line is square 1, and this line of slope 1/2 is square 2. Now this is acting on the cohomology of the sphere spectrum. There's the 5-pointed star. Now, the homology of the sphere spectrum, the gratings are turned around, and the Steenrod operation's lower degree, but otherwise the picture is the same. So it looks like this. Now, okay, so now I'm going to describe the Dualsteen algebra. So here's the description that you've seen before. This is the classical Steenrod algebra. So it's a polynomial algebra on the elements known as x's, and this is the coproduct formula. This is the formula you've seen many times. Now, for notational purposes, I'm going to rewrite it like this. I'm going to call the polynomial generators tau. I'm going to replace tau ci by tau I minus 1, and I'm going to rename the x's up. The x's here stand for the squares of the x's up here, and each xi is the square of the previous tau. So this is another way of writing the same algebra as before. So I've changed the notation a little bit. Okay, so this is another way of writing the classical Dualsteen algebra. I haven't done anything equivariant yet. And there's a similar description at odd primes with the understanding that tau I squared is 0 at odd primes. Okay, now, so this is the classical Steenrod algebra with this new notation. And now I'm going to tell you how to modify it to get the equivariant Steenrod algebra. So for one thing, we'll have to replace this z mod 2 by the homology of a point, this m star here. That means instead of a Hopf algebra, we have a Hopf algebroid, and that means there's a right unit in the picture. And so I have to tell you how the right unit acts. So the right unit of A is A, and the right unit of U is U plus A tau naught, which I will abbreviate by U bar. Now, so now the degrees of the generators have to be changed appropriately as indicated here. And most importantly, the multiplicative relation gets changed. In the classical case, we had that the square of tau I was equal to ci plus 1. Here, the square of tau I is this. And I see this, let's see, this should have been red. I knew this would happen. This U should be red. U's are supposed to be red. That's a typo. That's a color typo. A chromatic typo. And as before, if you were to set A equal to 0 and U equal to 1, that would mean U bar is also equal to 1, and so we'd get the same thing that we had up here. Oh, here I've got the colors right. Okay, so this is the Dualsteen algebra for the C2 equivariant world. So the main feature is that these multiplicative relations are not what you could have guessed. There's some information there that you don't have in the classical case. Now, you could try to compute the X group of this. And of course, this is very complicated. It's at least as hard as calculating the X group for the classical Steenrod algebra. That is calculating the E2 term of the classical Adem spectral sequence, and we all know how much fun that is. So that's prohibitively complicated. So as in the classical case, you do a warm-up exercise by replacing the full Steenrod algebra by something smaller, like the subalgebra I just described, and try to calculate its X group. So I want to tell you what the dual of this A1 is. So in the classical case, you take A star and kill off certain powers of generators. So you get this. This is the classical A1 star. And equivariantly, we'll have a similar description, but you'll have this funny multiplicative relation in there instead of this one. So this is the dual of the C2 equivariant A1. This is the algebra that this talk is about. Now, remember the coefficient ring itself is the polynomial algebra on A and U plus this negative cone. And I'm not going to say much about the negative cone, but so the real motivic coefficient ring is the same as the C2 equivariant one without the negative cone. So in that sense, C2 equivariant homotopy theory has more information than real motivic homotopy theory because we have the negative cone and they don't. Whoopee. Okay, so there's two ways you could make this a little simpler. One is you could declare A to be invertible. And there is a equivariant construction that was related to that has to do with geometric fixed points, but I don't have time to go into it. So let's just say we're going to formally make A invertible and see what happens. Now, this will kill the negative cone because everybody in the negative cone is A torsion. Everything in the negative cone is killed by some power of A. So if you invert it, that means you wipe out, inverting something wipes out all the torsion. So inverting A eliminates the negative cone, so we don't have to worry about it anymore. And it means there's a four-term exact sequence like that, but I'm not really going to use that. Now, more importantly, this multiplicative relation here can be rewritten like this. You can, since you're allowed to divide by A, you can say that tau 1 is equal to this. So tau 1 is now redundant as a generator of the ring. It can be expressed in terms of tau 0 and C1. So that simplifies the dual algebra quite a bit. And the right unit formula becomes this, and the X calculation here is actually quite easy. I don't have time to go into the details, but I'll tell you what the answer is. This is the answer. So you end up with the fourth power of u shows up in the X group, and also you have a polynomial algebra on H1. H1 is this guy, and in the classical Adem spectral sequence, H1 is the element that detects the Hopf map. That detects the Hopf map in the homotopy groups of spheres. Now remember, I told you early in the lecture that the fourth power of the Hopf map is 0. But in the equivariant world, no power of the Hopf map is 0. And that's why we get this H1 here isn't truncated. All powers of H1 occur in this X group. And that is related to the fact that the Hopf map isn't nilpotent equivariantly. Now, the other way we can simplify this calculation, we could also kill A. We could set A equal to 0. That's another way to make this simpler. Now, doing that, that will also kill the negative cone, but for a different reason. Inverting A killed the negative cone because everybody in the negative cone was A torsion. Setting A equal to 0 will kill it because everybody in the negative cone is divisible by A. So if you set A equal to 0, that means you're making everybody you're making the negative cone go away. So the negative cone disappears in both of these simplifications, but for two different reasons. Remember, I've told you several times that if you set A equal to 0 and set U equal to 1, you're in the classical case. And in the classical case, we've known for a long time what this X group is. So here's the familiar chart. I hope you've seen this before. So this is a chart that's related to the homotopy of the KO spectrum and so forth. Anyway, this is the classical calculation of the X group for the classical A1. Now, the motivic answer, so here it is again, and now I'm going to describe it in terms of generators and relations. There's an element H0 right here, H1 is here, and these two generators I'm calling alpha and beta. And here they are. Here's generators and relations. Here's the thing described as a ring with generators and relations. And here's a description of exactly what all these elements are. Alpha and beta are certain Massey products indicated here. I'll quiz you on all this later. I hope you've got 10 seconds to memorize all this. So we're in the setting A equal to 0 but not doing anything to U is equivalent to passing to the complex motivic case. So that's where we are now, the complex motivic case. And the answer is only slightly different. And the difference is that whereas we had h1 cubed equals 0 up here, in this case it's U h1 cubed. Otherwise, everything is exactly the same, except the gradings are a little different. For example, this element beta is defined as a Massey product like this. It lives in this X group. Up here, it's defined like this and lives in that X group. But the primary difference is instead of h1 cubed being 0, U h1 cubed is 0. And h1 itself, no power of h1 is 0. And again, that's related to the non-nilpotence of the Hopf map that I showed you before. So here's a picture of it. Here's a picture. So these red diagonal arrows indicate towers of elements related by H1 and killed by U. And other than that, it looks pretty much like the previous picture. So what have we done? This is what we get by killing A. Now, if you want to get the original answer back, you have to run some sort of Bachstein spectral sequence involving A, and blah, 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 blah. I'm almost at the end here. There is a Bachstein spectral sequence, and it has 3 differentials, God help us. And this leads to a ring with 9 generators and 22 relations. I'm sure you're on the edge of your seat. And, and if you bring the negative cone into the picture, it gets even more complicated. And this is a good place to stop. Thank you. Mark, yes.
Is there a spectrum that a C2-equivariant?
Yes, there is. Yes, there is a C2-equivariant spectrum that's an equivariant analog of KO, little ko, and this calculates its homotopy. Yes, there is.
So your computation, you inverted A, seems to suggest that the geometric fixed points of that spectrum is a wedge of various powers of the equal number of planes of the
No, you've got all these H1s in it.
Yeah, but there's A, so you multiply.
What?
There's the H1s, aren't the H1s living in weight non-zero?
Yes,
So we
but
can multiply them by power of A to put them in zero, right?
well, maybe you're right. I'm not sure about the answer to that. So you're saying that the geometric fixed points of this equivariant KO might just be a wedge of HZs. You could be right. I'm not sure.
Okay.
My co-authors would know better. Jack.
I think somebody should figure out what functor the dual half algebra represents. I've tried a lot to do it, and I get mixed up, in particular because I had the Cartan formula.
Well,
Somebody with a clear head could do it, I think.
I don't know. I have no idea. Yeah. Oh, his question, he says that someone should figure out the functor represented by the Dualsteen algebra. So I think this is a question, the functor in the sense of abstract algebraic geometry. That's been done. In the equivariant case? In the motivic case. Who did it? Oh. Is this a Harvard student? Okay, there you go. It's been done at Harvard.
So, are you guys going to put out a little VO resolutions next?
I don't know. I don't know.
Any other questions? All right. Yep.
Do you know of an analog for standard algebra for other groups like CP?
Not off the top of my head, no. I don't know that that's been done. I don't know if it's been done for CP, so you could work on it.